So good morning everyone. So for our lecture today, we're going to go into the second section of our topic root locus. So we're going to look at how to sketch a root locus. So what does it mean to sketch a root locus? So uh, at the end of this video lecture, what we expect you will be able to do at the end of it is the first one is to apply several rules that we learned to sketch a root locus. So what's the difference with what we have done previously in the introduction of root locus? What we did was basically plotting the root locus manually by changing the value of k one by one from 0 to a certain value that we consider very high enough, right? So we, for example, in the characteristic equation, we put k equals to 0, k equals to 5, equal to 10, and so on and so forth. And then we plot the position of the poles according to that value of k. But we don't want to do that because that would take an important amount of time. So what we would like to do is basically to sketch it, to sketch the root locus without going point by point. And there are certain rules that we can apply when we observe that behavior of plotting it manually. There are certain rules that come out, and we're going to learn those rules, and we will be able at the end to sketch a root locus, right? And then secondly, it's not just sketching it. We will be able to also at the end apply some additional rules that we will introduce to refine the sketch of the root locus. So basically the thing that we're going to refine is several points. The points are on the root locus that we want to refine are we will explain more in depth later. So we'll be able to find what we call as the real axis break weight, the real axis breaking points of the root locus. We'll be able to find the j omega axis crossing. This is a very important point. We can see from previous slide that this is the point where basically on the j omega axis crossing, it is the limit when we will have our system. If it goes beyond it, then it goes to the right hand side of our S-plane, then it means our system will become unstable with that value of k, right? So we'll be able, with certain rules, find this j omega axis crossing, its value, and then finally we'll be able also to find the angle of arrival and angle of departure. This might be less important, but it could be done as well to have a very precise root locus, okay? So in this subchapter, these are all the things that we're going to look at. So before we go into each chapter, each point of this section, what we're going to do is we're going to review very briefly, very quickly about root locus. So what is root locus? In terms of textbook definition, root locus is the path of the roots of the characteristic equation. So it's the path of the roots or the roots of polynomials, or we can call it as the poles of the characteristic equation traced out in the S-plane as a system parameter is changed. So the system parameter that we're going to be interested in changing here is just again k for the moment, right? So what is the characteristic? So imagine this is your complete system where you have a forward transfer function of gs, you have a gain that you add to it that you call k, and then you have a feedback transfer function of hs, right? So what we're going to do is that in a root locus, it is going to be taken for the whole system. So if we take it for the whole system, what you need to do is to simplify it to find an equivalent transfer function, a single transfer function. So you know it by now, it's gs over 1 plus kgs hs. You can develop it, so etc, etc. And then you'll find it that basically at the end, what will characterize your system is the denominator. It's the thing that we have at the bottom of our fraction, right? Because it is the part that will give the poles of our system. So this is what we call, again, this is what we call the characteristic equation of a system. It's 1 plus kgs hs. So for this particular system that we've presented in previous slide, when you do the calculation, it is these terms: 1 plus k s plus 1, s plus 3 over s plus 4, s plus 5, s plus 2, right? So the characteristic equation is this, and if you want to find the root of this characteristic equation, it is basically, it is when it is equals to 0, right? So the characteristic equation is is this part. So we have developed it. So it becomes s plus 2, s plus 4, s plus 5 plus k multiplied by s plus 1 multiplied by s plus 3. If you want to find the position of the poles as k varies, it is basically the condition of these polynomials equals to 0. So let's see. What we did previously was basically we try to find the position of the poles as k varies, right? For example, for a k that varies from 0 to infinity, let's say we take k equals to 0. Okay, so now k equals to 0, so the equation becomes so and so. So for example, in this case, it will become s plus 2, s plus 4, s plus 5. This term all will disappear. So we will be able to find the poles at k equals to 0. So that's the first position of the poles as k equals to 0. And then we change k equals to 5, 10, so on and so forth. But the real root locus is when basically we want to see all roots of the characteristic equation as k varies from 0 to infinity. As k varies from 0 to infinity continuously. So the root locus, we can say that root locus starts at k equals to 0 and it ends at k equals to infinity. So it is a curve, it is a tracing, a plot of several lines that represent the position of the poles, the position of the roots as k goes from 0 to infinity. So now I think we have reviewed enough of it, so we can tackle the sketching part. Okay, so let's take a look concretely at the application of the root locus on our previous system. So the system basically so I put here again. So we put here again the characteristic equation of the system that we had in previous slides. So this is the characteristic equation. So what is root locus? It is basically plotting the position of the poles as k goes from 0 to infinity. So let's take an example. We'll take the two cases of extremities. The two extreme cases are, of course, at the beginning and at the end. Beginning at k equals to 0, ending at k equals to infinity. So let's take a look at our characteristic equation. Replace k equals to 0 first to see where does our root locus begin, right? Because k equals to 0 is where the root locus tracing begins. So if k equals to 0, so we'll have this term as 0, and the only terms that left in our characteristic equation is these three terms, s plus 2, s plus 4, s plus 5. Therefore, our position of poles, there are three poles, right? And one is at minus 2, another one is at minus 4, and the last one, the third one, is at minus 5. So it's written here, P1 minus 2, P2 minus 4, and P3 minus 5. So let's say we plot the, let's go and plot the position of the poles at k equals to 0. So here you can see it's marked with X or cross here at minus 5, minus 4, and minus 2. So minus 2 being the first poles, P1, minus 4 is P2, and minus 5 is P3. Okay, so in X's, basically in this cross are the position of the poles of our characteristic equation as k equals to 0. So what about another extreme case where k equals to infinity? So if k is equals to infinity, what happened to our characteristic equation? So we can see that when k equals to infinity, so these terms will become very, very high, very, very big in comparison to these three terms, s plus 2, s plus 4, s plus 5. So we can say that we can neglect this term because this term is huge, is far bigger than these terms on the left. So we can say that k multiplied by s plus 1 multiplied by s plus 3 equals to 0, right? So if we have so, it means we will have basically how many poles we have. We can see there's one at minus 1, there's another one at minus 3, and we basically have another point, P3 at infinity. P3 at infinity. So there we go. At k equals to infinity, we have P1 minus 1, P2 minus 3, and P3 infinity. And if we take a look at this P1 minus 1, P2 minus 3, and P3, these terms, k multiplied by s plus 1 multiplied by s plus 3, this term, if we look at our system, the origin of system, this is basically our zeros. These are the terms that is located in our system at the numerator of the fraction. So s plus 1 and s plus 3 are basically the zeros. So the minus 1 and minus 3 are written here, are marked here with these zero symbols at minus 1 and minus 3. And then there's another one at infinity. We don't know where the position is. So it is not noted over here. What we can see is there's two things. We know that the position of the poles at k equals 0 to 0, it begins at minus 5, minus 4, and minus 2. And as we increase the value of k, as we did in last week's exercises, we increase the value of k, let's say 5, 10, 20, 50, and so on and so forth. The position of the poles will change, will varies. So it changed from minus 2, for example, let's take these poles. It changed from minus 2 and it moved into a certain direction. From minus 4, it moved into a certain direction, and from minus 5, it moved into a certain direction. And these three poles will at the end goes to a certain value, right? And the value onto which it goes is basically from here we have demonstrated that all the poles, when k increase, it will tend to goes toward a zeros. So for example here, the poles of minus 2, it will tend to goes towards, when it is equals to infinity, it will goes towards minus 1. This minus 4, it goes towards minus 4. Minus 5, it goes towards minus infinity. So we can see there's a pattern here. It starts from poles and it goes towards zeros of our system, right? So this several pattern that we see, basically in automatic control, they have created a few rules with this observation. They have listed several rules that we can use in order to directly sketch our root locus without going to do manually changing k one by one and finding the poles as k varies one by one, right? So these are the things that we're going to learn. So as I said, there are certain rules, and here we go, the first rule, in order to sketch our root locus. The first rule say that the number of branches of the root locus equal to the number of closed loop poles. Okay, the number of branches. So what is branches? Let's see. So the branches this is an example of what we have seen in last week lecture. So we have basically two poles that start at 0 and start at minus 10. And there are branches that goes from minus 10 towards minus infinity in this direction, and from 0 to plus infinity in this direction. These two arrows here, this 1 and 2, we call it as branch. So we have first branch, we have second branch. So the branch are presented here. It's better if you can present it in different colors. Let's have a pen and I'll present it in different colors here. So imagine, so basically starting from 0, oh, I'm sorry, can I erase this? Up. Okay, let me take back my pen. So basically it goes from zeros and up into this direction. This is what we call one branch. Another one, if I can get another color, so another one that start at minus 10, it goes in this direction and it goes to minus infinity. So these two, the red and green lines, is what we call branches. So what does the first rule says? The first rule says that the number of branches of the root locus equals to the number of closed loop poles. So if you have your closed loop system, the number of poles of your closed loop system will show you how many branch will you have, right? So that is the first rule. We'll just go through the rules and then later we'll try to do an example to make sure that you understand the application of all the rules. Rule number 2. So what does the rule number 2 says? It says that the root locus is symmetrical about the real axis. It is always symmetrical about the real axis. So if we look at our root locus of our previous system, there's one that goes this direction, there's another one that goes this direction, and if you look at all the branches, so we have 2 branches, and the combination of the branches is basically it's a cross like this. It's like a plus symbol, right? And this tracing or this sketch is symmetrical about the real axis. It's symmetrical when you look from the point of view of real axis, right? From the point of view of real axis or sigma axis, the root locus is exactly symmetrical. If it is not symmetrical, then there's something wrong with your root locus. You have plotted a wrong root locus, right? The third rule. So the third rules can be sometimes very confusing. So the third rule says that on the real axis, so on sigma axis, for k larger than 0, so for your gain larger than 0, the root locus exists to the left of an odd number of real axis. So it exists to the left of an odd number. So the odd number here are -1 and -3. So the root locus tracing is basically always on the left of the root locus. And then exists to the left of an odd number of real axis, finite open loop poles and of finite open loop zeros. So what it says that is basically it is on the left of the it's on the left of an odd number, but this is exclusively for finite open loop and finite open loop poles and finite open loop zeros. So basically for the branches that doesn't goes towards infinity, for example in the example that we have stated in this in the early of this lecture, there is one pole that goes towards infinity, that it doesn't apply for that. But for all the branches that is finite, like this, that is finite, the branches is actually located on the left hand side, on the left of an odd number, right? So that's rule number 4. It says that the root locus begin at the finite and infinite poles G, S, H, S and ends at the finite and finite zeros of G, S, H, S. So we this was pretty clear in the example that we had just now, right? So when k equals to 0, we get the poles, and when k equals to infinity, we'll get the zeros. So it's always start at the poles, right? Begin at the finite and infinite poles and ends at the finite and infinite zeros. So it start at the poles and it always end at a 0. So for example here is basically we have two two poles, -2 and -1. Our closed loop system have two zeros, -4 and -3. So they both will start at poles and they both will end at zeros. So the first one is basically, if I can get my pen, let's say we take a color. So the first poles is, it could be so one at -2, it start here and it goes toward here, -2 to -3, and the other poles could be -1, it goes in this direction, and then it goes to -4. So these are, there are two branches. It all start at poles and it all ends at zeros. You cannot have something that start at poles and at poles. It start at poles and always end at the zeros. And if you look at the example of this particular root locus, it basically it agrees with all the previous rule that we have seen. So for example, the first rule we cannot verify because it says the number of poles equals to the number of branch. We don't have the equation over here, so we cannot verify that. But as for rule number 2, for example, it says that it should be symmetrical. We can see that it is symmetrical about the real axis sigma. And then the third rule was it is on the left of odd number. So we can see that the poles on real axis are always on the left of the odd number as well, right? So this is rule number 4, and it is basically the first rule that we apply because it's the easiest one. It's the easiest one and it's the most obvious one. So what is the rule? Again, the rule is root locus begin at finite and infinite poles. So it begins at poles and it ends at finite and infinite zeros. So it ends at a 0. And then we have the final rule for simple sketching. The rule says that the root locus approaches straight lines as asymptotes as the locus approaches infinity. Okay, the root locus approaches straight lines as asymptotes as the locus approaches infinity. So this is for basically for infinite zeros, as in our example just now, when we have poles that goes as k goes to infinity, it goes to infinity. It goes to infinity not by it goes towards infinity following a certain rules, and the rules is that it goes approaching straight lines as asymptotes. So what is the equation of that straight lines? The equation of the asymptotes is basically there are two parts. The first part is uh, the real, what we call the real axis intercept. So there is an equation to find the real axis intercept of the asymptotes. So this will be clearer when we do an example, right? So the real axis intercept is basically the point on which we will have the intersection of all those asymptotic lines. So this real intercept, we call it as sigma A because it is a position on the real axis, sigma. It is equals to the sum of finite poles minus the sum of finite zeros divided by the number of finite poles minus the number of finite zeros. We'll do an example to make it clearer. And then there's another thing, it's not just having the point on which the asymptotic line intercept or starts, we will also have an angle of that asymptotic line, and the intercept angles equation is given by theta A equals to 2k plus 1 multiplied by pi divided by the number of finite poles minus the number of finite zeros. It is very unclear, cluttered for the moment, but we'll go into an example to make it clearer later, right? So here let's take a look at the example of application on which the poles goes towards infinity. Therefore, we need to be able to plot basically what we call the asymptotic line on which the the root locus sketching of the poles that goes towards infinity will tend to go closer and closer to, right? So imagine we have this system with a transfer function, a forward transfer function, and over here, and the feedback transfer function is a unity feedback transfer function. Here we have the gain k that will varies, and then the gs is basically this part, s plus 3 over s plus 1, s plus 2, s plus 4. So what do we do first? The thing that we do is, of course, if we do it one by one before we going into the asymptotic line, we can see that there are 4 poles. If k equals to 0, there are 4 poles and there's only 1 0. So here we go. Again, I repeat the process. So if you look at the transfer function, we see that from the denominator, we have four poles, s plus 1, s plus 2, s plus 4. That gives us basically a poles of, if we look at our S-plane here, the plot of what we could call as PZ map, pole 0 maps. We have the poles at 0, at minus 1, at minus 2 and minus 4. So there you go, 0, minus 1, minus 2 and minus 4, right? So from one of the rules in the sketch of root locus, we know that it was rule number basically the first rule says the number of roots will show you how many branch do you have. So basically there will be 1, 2, 3, 4 branch, and all the branches basically in another rules it says it start at poles and you end at zeros. But when we look at the numerator, we can see that there's only one possibility of zeros, which is minus 3. So here we have the zeros at minus 3, the only single zero at minus 3. So what does this mean? It means that there will be only one poles that will be able to go to these zeros. But as for the other poles, the root locus will goes towards infinity, right? It will goes toward infinity. So if you look here, we have 0, minus 1, minus 2, and minus 4. The only possibility for the roots to goes towards a 0 is basically from minus 2 or to minus 3. Because let's say if we take 0 and minus 1, a root locus, the branch of root locus cannot goes across another roots. For example, the minus 1, if it wants to go towards minus 3, the sketch, the branch will go across minus 2. That cannot be done. So that's also the case for 0. What about for 4? As for minus 4, if it goes to minus 3, what happens is that minus 2 have to go somewhere else, and the minus 2, if we want to go to somewhere else, the only way it can go is basically it's into infinity. But we know that if it goes into infinity, it will follow an asymptotic line, and later we will see why why do we make this decision. Is because when we have three roots that needs to goes into three zeros, one of them will go into one of the zeros, one of these only single zeros. Therefore, there will be three asymptotic lines, and when we have three asymptotic lines, usually the asymptotic lines are divided in between 360 degrees. So if it is divided in 360 degrees, the only possibilities to go is basically to go 360 degrees divided by 3, that will make 120 degrees. It will go in the direction of 120 degrees. So we can see here is basically it is already traced the asymptotic lines, but we'll see how do we find this. It will either go to these asymptotic lines, this one or this one. As for minus 2, basically it has no other choice rather than going to the 0. Why? Because the minus 1 and minus 0 cannot go to the 0, so it has to follow these two asymptotic lines. As for minus 4, it has to follow another asymptotic lines. Basically, there is an asymptotic lines here at minus 180 degrees. The minus 2 cannot go to minus 180 degrees, because if it do so, then it have to go across minus 4 and minus 3, right? So let's have a look. How do we construct these asymptotic lines? So the asymptotic lines that we're seeing is basically it's this line, and there's another line. We'll see step by step. So the first thing in order to find the asymptotic lines is basically to find what we call as intersection point. It's noted as sigma A. What is intersection point? If you look at the asymptotic lines, there's a point where all the asymptotic lines intersect. So that's what we call as the intersection point of asymptotic lines. So there is a formula to find that coordinates on sigma axis. It is equals to the sum of finite poles minus the sum of finite zeros divided by the number of finite poles minus the number of finite zeros. Let's see. For our transfer function, therefore, what are the poles? we can see that the poles is basically it's 0, -1, -2, and -4. So the sum of the finite poles, the sum of the finite poles, or the sum of poles, simply, the sum of poles is the sum of -1, -2, -4, -0, minus the sum of zeros. And the sum of zeros, you know that the zeros that we have here is -3, so it's -3 divided by the number of poles minus the number of zeros. So what is the number of poles? How many poles do we have? We said just now it's 1, 2, 3, 4. 4 minus the number of zeros. There's only one zero, so -1. So you can see doing this calculation, you get the coordinate of -4/3. So here, this point is basically the point at the coordinate of sigma axis -4/3. So that is our intersection point sigma A. So basically, when you do that, you imagine you don't have yet these asymptotic lines, these three lines, which we call asymptote line. You will be able to first, before having this, you'll be able to find this point of sigma A. Therefore, you know that you have lines that all crossing this will intersect at this point. Next, what you need to do is, now we have the point where the lines begins, let's say, and we want to know in which direction does the line goes. Here we can see that it goes in this direction, but how do we decide that it goes in this direction? So that is another calculation. That is basically the calculation of the angle of that asymptotic line. We call it as theta A. So the calculation is basically, this is basically the application of the rules that we have learned in previous video lecture. So it is 2k plus 1 multiplied by pi divided by the number of finite poles minus the number of finite zeros. Let's see how do we apply this. So basically, the first thing is to identify what's the value of k's. Right? What is the value of k's? So what is the value of k's? Value of k's depends on how many poles does need to go into infinity. So here we have 4 poles. We have 1 zeros. So 1 poles can go to this 0, but there are another 3 poles that need to go to infinity. So 3 poles need to go to infinity, therefore k equals to, well, k will have 3 values. So the 3 values of k are basically k equals to 0. It is an integer starting from 0. K equals to 0, k equals to 1, and k equals to 2. So you do the calculation of theta A, you have 3 theta A with k equals to 0, k equals to 1, and k equals to 2. So for all those 3 cases, k equals to 0, k equals to 1, k equals to 2, if we do this calculation, so the number of finite poles, the number of finite zero is the same as we had here. It's 3. So you'll find that theta A equals to, for k equals to 0, equals to pi over 3, equals to pi, and equals to 5 pi over 3. So it's basically 360 degrees divided by 3. So therefore, we find the direction of the first theta is this line, pi over 3. The second one is this line, pi, right? The angle is pi. And then the third one, so the angles basically, you know, I assume that you know that when you indicate the angles, it's in reference to this axis, sigma, and you start 0 angle at this axis as you increase. So here, when you got here, it's 180 degrees. So that's why pi over 3 is this direction, 180 degrees is this direction, and 5 pi over 3 is this direction. It's the equal of minus pi over 3, right? So these are the 3 asymptotic lines that you will trace. There you go, the asymptotic lines. Therefore, once we have that asymptotic line, what do we do? Once you have the asymptotic lines, you know that one pole of -2 goes into -3. So therefore, the other 3 poles, what do we do? -4 is trivial. It's quite evident that it will goes toward -infinity. As for 0 and 1, 0 and 1 will basically the other rules is one of the other rules is that the root locus sketching need to be symmetric. So in order for it to be symmetric, what will happen is that the -1 and 0, it is like in one of our previous exercises, it will goes to a center point, meet at the center point, and it will split up into 2 directions, one towards j omega positive, the other one towards j omega negative. So one will go on the upper side, the other one will goes to the lower side. So this part here on the top will goes closer and closer towards the asymptotic line. So what does it mean as asymptotic lines? As basically as k goes towards infinity, these lines this branch will go closer and closer and closer, and it will look as if it is a straight lines that will goes closer towards this asymptotic lines. And the same will happen for this branch as well, as it goes towards minus j omega. So there you go. The plotting of root locus for the cases where we have basically the poles that goes towards infinity, and this is how we sketch the direction of it by finding the asymptotic lines. So to find the asymptotic lines, there are 2 points. Find the intersection point and find the direction or the angle of those asymptotic points, right? So after this, we'll go through, in another video lecture. So now we are establishing all the rules, but in the next video lecture, we will go through a few examples, right? So there are 3 other rules. The 4-5 rules that we have stated just now are basically the rules that are the most basic and the most important one to let you to sketch pre-sketch root locus branches. But there are 3 more rules that you need in order to refine the sketch. So this part we call it as refining the sketch. There are 3 more rules. The first one is basically what we call a real axis breakaway and breaking points, right? Well, I'll start with the first one. So the first one is basically finding the j omega axis crossings. So what is j omega axis crossings? J omega axis crossing is basically, if you look at the example, let me take my pen first. If you look at the example that we had previously, right? So this is j omega axis. This is sigma axis. We had basically 2 poles that has, if I can have another color. We have 2 poles that goes in this direction, and then they split up following an asymptotic lines. So this is, let's say, branch 1, this is branch 2. They cross. What happened is there is a certain point where it will cross this j omega crossings. So these 2 points is what we call the j omega axis crossings. So if you just apply the 4-5 rules that we have learned previously, just now, those rules will let you know that, well, there is a point sigma a, and then there are asymptotic lines, so the branch will goes closer and closer toward the asymptotic line, but you will never be able to know at which point of j omega axis will it actually cross the j omega axis. So therefore, in order to refine the sketch to make it more precise, there are rules that we will learn in order to be able to pinpoint the point on which the branch will cross the j omega axis. So that's the first one. This is basically the most important one because it have a direct consequence on the identification of stability of the system, right? Because this point is the point on which, if it goes beyond it, then the system will become unstable because it goes towards the right side of the S-plane, right? So we will particularly learn this because this is a very important rules. But as for the other rules, basically 2 and 3, I will let you learn it on your own because they are less, we would say they are less important compared to the first one, right? So the only thing that you want to achieve, the thing that we want to achieve in root locus for this course is basically for you to be able to plot the root locus and then to identify the j omega axis crossing, and then the rest, if they are not refined, it is still okay for the moment. So the 2 others that you can learn on your own if you wish, which I strongly suggest you to have a look at it because it is not that complicated. The second one is basically to find the real axis breakaway and breaking points. So basically, what is a real axis breakaway and breaking points? Breakaway and breaking points is this point on which the branch split, or in where the branch get into. So this point is what we call the breaking point. For example, if we use just the 4 rules that we had we have seen just now, we won't be able to identify where is this point. We might think that it should be in the middle, but we don't know exactly where it is. By using these rules, you will be able to pinpoint where is the point where it start to breaks away or breaks in. And then the third one is basically the angle of departure and arrival. So this angle here, so basically there is an departure angle on which we'll be able to plot to identify, to calculate the tangent of this curve, on which this curve will depart from the break-in or breakaway point. So this is what we call breakaway point, right? So the angle on which this branch will depart, that is what we call angle of departure or arrival. So there is a method as well, the rules, in order to be able to identify, to define, to refine how will this breakaway or break-in angle be. It is in this point 3. So I'll suggest you to do that. But for the moment, we will concentrate on the j omega axis crossings. Okay, so now let's talk about the rules, the first rules on refining the root locus, which is the j omega crossings. Let me get my pointer first. Okay, so let's see. This is a root locus that has already been traced. So it should come from basically a system with a certain transfer function, a certain gain. There is gain, of course. Here we will only treat the case where the gain is k alone, and then it should have a feedback transfer function as well. But at the end, it looks like this. So before that, let's have a look at the application of the first 5 rules that we have learned, right? So for example, from here we can see that there are basically so what are the rules? Let us establish that first. Let's see, I'll get a black ink, and the rules are can you if you can basically tell us what the rules are. The first rule is basically the number of branch. Just to recall you, number of branch should be equals to the number of your poles. And then, so if you look into this example, how many branch do you see? How many branch do you actually see? There are actually number of branch equals to number of poles. So the thing that we want to identify is what are the poles. So we can see this is a PZ map. We can identify basically 2 poles and 2 zeros. So there are basically 2 poles. So if there are 2 poles, it means there should be two branches of this root locus. Where are the 2 branches? Let me get another color. So basically the branches are, there's one over here that start at -2, and it goes all the way probably to 3. And the other one, if we take another color, the other one is the one that start at -1, and then it goes all the way to 5, right? So there are 2 poles, therefore there are 2 branch, and the branch are basically the one in red and the one in green. So those are the 2 branches. And then if we recall the second rules, what is the second rules? Second rule says that they should be symmetrical. The root locus, the sketch of a root locus should be symmetrical. So here we can see that it's completely symmetrical. If you don't know how to, basically if you have only if I get my pointer back to show you. So basically if you get at the beginning, when you plot the poles and the zeros, you got -2, -1, 3 and 4. You don't know in which way you go to. What will happen is that the first rule say there will be 2 branch, okay, that will be no problem. The second one is you know that it has to be symmetrical. Okay, now you don't know yet how to plot it, but it has to be symmetrical. So let's take a look at rules number 3. Rules number 3 says it is to be symmetrical. Number 2 it says it have to be symmetrical, but number 3 says the finite branch is always on the left on an odd number. So this is a very specific. You don't have to always take into account the third rules. Left of an odd number. This is only applies for the case where you don't have where the branch are all finite. What do I mean by this? In this case, this is the case where we have this, right? All the branches are finite. What does it mean? It means that when you have two poles, you also have two zeros. When you have two poles and two zeros, it means, so we have to go to rules number 4 as well in order to do this. And the rules number 4, it says that every poles, every branch start at poles and it end at zeros. It start at poles and it end at zeros. So if you have two poles, then it will end at the two zeros. But you have two poles but one zeros. One will end at one zeros, and the other poles will end at infinite zeros, which make it an infinite branch. But now here, in this case, all two branches are finite. Right? All two branches are finite. Why? Because we have two poles and two zeros, so all the branches will have an ending at these two zeros, right? So if they have an ending at two zeros and both of them are finite, if both of them are finite, then the third rule applies. If the branches are finite, then all the root locus will be on the left side of the odd number. So we see here the odd number is basically -1 and 5. So the root locus on sigma axis, it is situated here on the left side of the odd number. So it will not be in this part. So it is not in this part, only on the left, and it has to be symmetrical as well. So that's why we know that somehow it will have a departure point, what we call departure point, and it goes one to the top side, the other one to the bottom part, and it will rejoin at another point. So this is what we call breakaway point. This is a break-in point, and they'll go to each zeros, which are 3 and 5, right? So this is basically the application of the 4, 5 rules. Well, basically there's another rules. The fifth rule, if I can write them, the fifth rule is basically for the rules where you don't. So it's either 3 or 5. The rules of 5 is basically applied for infinite branch. Infinite branch. If you have basically more poles than zeros, it means you will have infinite branch. And what happens to the infinite branch? Infinite branch will goes towards an asymptotic line, and that asymptotic line, of course, we have seen, in order to find those asymptotic lines, you need to find sigma A, which is the intersection point, and you need to find theta A, which is the angle of that asymptotic lines, right? So these are basically, before we start the j omega axis crossing, these are basically the application of the 5 rules, the basic rules that we have established just now to be able to plot our root locus sketch. So this is the sketch of the root locus. But now what we're interested in is basically these 2 points. That's what we call j omega axis crossings. You want to know what is the value of these points in order to be able to plot properly, to trace properly, to sketch properly our root locus. Because we might draw it over here or over here, right, or even lower, but it is specifically on a certain point. It crosses on a certain point. That's why we want to find out where is that j omega axis crossing. So j omega axis crossing is basically the point that separates between stable and unstable system. It is a very important point because we know that if you start to be located, your poles start to be located on the left side of the S-plane, you will be having an unstable system. So it is the point that separates between stable and unstable systems. So those are the 2 points that we're looking for in these particular rules. So now let's take a look at an example. How do we find exactly this j omega axis crossing? How do we find exactly this j omega axis crossing? So in order to do that, let's take an example of a system where we will have basically this j omega axis crossing. So here, how do we find it? It's basically we will use one of the criteria that we have used previously in order to define the stability of a system, which is Routh-Lewis criteria, right? So imagine this is the transfer function of our system. We can see from the transfer function that basically we have 1, 2, 3, 4. We have 4 poles, and we have only 1 zeros. If you have 4 poles and 1 zeros, it means, what does it mean? By applying the rules that we've seen just now, the 5 rules, 1 pole we goes into these zeros. It is basically the thing that we have plotted previously. You can goes back to that particular page of the slide and refer it. And then there will be 3 other poles that will goes into infinity. And then if you remember, there will be 2 poles that will cross j omega axis crossing, right? And the poles are basically the poles at 0 and at -1. So please refer to that examples in previous slides. The -2 will goes to -3, -4 will goes to minus infinity, and the -1 and 0 will tend to goes toward infinity in a certain direction, following an asymptotic line, and they will cross the j omega axis crossing. So we want to find the crossing on which these two branches will cross the j omega axis, right? So in order to do so, we use Ruth-Lewis criteria. So to use Ruth-Lewis criteria, again, as you remember, you have to simplify the system into one single equivalent transfer function. So here we go, we have the transfer function of a single block diagram. And then what do we do with it? So for Ruth-Lewis criteria, again, the characteristic equation is the equation that we have on the denominator of the fraction. So we put in our table of Ruth-Lewis. So the highest order is the order of 4. So we have on the column basically the first column the order of the polynomial s to the power 4 until s to the power 0, and then on each line you fill in with the coefficient of the polynomials. So we can see here, we will fill, if you remember, we will fill in the coefficient of s power 4 here, s power 2, we skip 1, s to the power 2, and then s to the power 0. Here is the coefficient to the s to the power 3, and then here is coefficient to s to the power 1. So we see here, s to the power 4, we got 1, s to the power 3, here we got 7, s to the power 2, we got a coefficient of 14, s, we got the coefficient of 8 plus k, and as for s to the power 0, we got 3k. So these are the coefficients of our polynomials, right? Of the characteristic equation. So what you do next is just you fill in the tables of your Ruth-Lewis criteria. So I'll let you revise a bit how do you fill it in. But at the end, you'll get, for example, after you filling it in, you'll get these values in those tables. So what should we do to find that this j omega axis crossing? So the rules is that in j omega axis crossing, we know that if it goes across j omega axis crossing, what happens is the poles are purely imaginary, right? If I get my pen back, let me get my pen. So if you are on a j omega axis crossing, so here we have j omega. Imagine just now your poles, so it goes like this, and then it break away and it goes like this, right? If you are located on this point, what happens is your poles are over here. Having poles here means you will not have a sigma component, you will only have j omega component. That means you have a purely imaginary roots. So purely imaginary roots only exist, the rule says that a purely imaginary roots only exists when there is 0 row. What does it mean 0 row? When your rows of your Ruth-Lewis criteria are completely 0. So we will verify in which row could it be possibly 0. Can this row be 0? No, it couldn't be 0 because the first two coefficients are 1 and 14. This one couldn't be 0 because there's 7 over here. Can this one be 0? If you want to make this particular row as 0, imagine if you put k equal to 0, so this one becomes 0, but this value here will become 90. So it is impossible to become 0. If you put here as 90, then this one will not become 0. So this is impossible to make it 0. So the purely imaginary roots can only happen here. Here, all the lines can be 0. Here is 0, here is 0. This cell can be 0 if the above, the numerator of the fraction is 0. So only row S1, so this row of s to the power 1, where we can entirely have the entire row as 0, right? So this is the row where it could be 0. So what do we do with it? So the thing that you do with the row where it could be 0, it will be 0 if minus k square minus 65k plus 720 equals to 0. So here we have the equation. So this is the condition to be at j omega axis crossing. So this equation is basically the condition for us to have a poles at j omega axis crossing, and it is only true if k equals to 9.65. So it is only true, this condition is only true if k, basically if you solve this quadratic equation, you get k equals to 9.65. So it is only true if k equals to 9.65. What does it mean? So I'll skip this first. We'll go to the conclusion. So the system is stable. We'll say that the system is stable. Well, basically k is the point where you are located on the j omega axis crossing. If I can draw back so that we can see it. So there you go, sigma j omega. We are here basically when k equals to 9.65. So, right? So it means that if you increase k, it will be in unstable area. But for k basically lower than 9.65, it is stable. So that's why in conclusion we say that for k from 0, because we always start k at 0, right? It's an integer positive. For k from 0 to 9.65, the system is stable. But for k equals to 9.65, so this is the condition to be located over here. For k equals to 9.65, what happens is the system is marginally stable. Because when we are located here, basically, we are always oscillating without any decay. So at k equals 9.65, the system is marginally stable, oscillating at, so this is another thing that you want to find out. So it will be oscillating at a certain frequency. What is the frequency? In order to find that, you have to do this, the second part of the rules. So basically, we have, in order to find that, what we need to do is we goes to the equation on top of this row. So on top of it, you have this equation, which is 90 minus k square plus 21k. So you construct this equation of 90 minus k s square plus 21k equals to 0, right? And then you replace k with, of course, 9.65, and then try to find the value of s, the roots, right? And then you'll be able to see that the roots is basically at plus minus j 1.59. So this is basically the value of that oscillation, or the value of that j omega axis crossing. Okay, get it? So the first part is basically to get the value of k. So there we go, we get the value of k. It will be at j omega axis crossing. It will be at j omega axis crossing for k equals to 9.65. And what is the value of j omega axis crossing? The value of j omega axis crossing is at plus minus 1.59. So this point, if I get another color, so this point is basically plus 1.59. This point is minus 1.59 j omega j, right? So this is basically the value of oscillation. So that's why we can say that here at k equals to 9.65, the system is marginally stable and it is oscillating at the frequency of 1.59 radian per second. There you go. We can now know the value of k at which it goes to j omega axis crossing, and we also know the point of that j omega axis crossing, which is plus minus 1.59, which is equal to the value of the oscillation. So that's the rules on refining the sketch to find the j omega axis crossing. So here is basically a quick plot using MATLAB. So here we can see the method to do it. So the equation is basically we key in back the equation that we had previously, and if you plot the root locus, a PZ map and root locus, you'll be able to identify the geometric axis crossing. If you click on this point, it will show that it's equals to J 1.59 and J minus J 1.59 at K equals to 9.65. Right? So that's how you find the geometric axis crossings. So there we go. I think we have finished with this part of video lecture. We have looked basically at the, to summarize, we have looked at the 5 rules, basic rules in order to be able to plot to sketch our root locus. And then we have particularly looked into one particular refinement, which is to find the j omega axis crossing. There are 2 other points after this that I suggest for you to study it on your own. They are less important than all the rules that we have stated previously. You can still have a proper sketch without having the two things that I haven't shown you, but I suggest you to look into it, which is basically the break-in breakaway point and break-in breakaway angle. So until next video, where we will look into several examples of root locus for you to be able to practice. Thank you and see you in the next video.